Hello everyone. Am I audible?
Yes, sir.
Okay, fine. So, can you see the screen? Hello.
It's visible. Yeah.
Yeah. So, okay, let's begin. So, good evening everyone. And today we have entered in the week 9 of our doubt and problem solving session of the course of techniques of material characterization. And in this week, we will be discussing mainly about some signals like X-ray, which is related to X-ray, like characteristics X-ray and continuous X-ray. And there are some more topics uh, which we will be covering in this session. So let's start. Yeah. So the first question is asking about the relationship between the voltage and whether it could be a wavelength or the intensity or the number of photons. So it is regarding the X-ray tube. So when we will increase the voltage of the X-ray tube, so what will increase? I mean, when if the voltage of the X-ray tube is increased, then what will happen? The intensity of all wavelength decreases, short wavelength limit shift to longer wavelength, number of photon produced per second increases, or the maximum wavelength position shift to longer wavelength. So, can you guess?
C.
C.
Number of photons.
Okay, fine. So let's see. Um, okay. So here, I think it is right. So here, as you can see, the voltage is increasing. So for an example here from the 5 kilovolt to 10, 15, 20, 25. So here in this way, the voltage in the X-ray tube is increasing, right? So the X-ray photon produced has a frequency lower than the Vmax and a wavelength longer than the this short wavelength lambda. So here, when the tube voltage is raised, I mean, when we will increase the voltage in the X-ray tube, the intensity of all wavelength increases. Okay, so here you can see the intensity. The intensity is also this y-axis is X-ray intensity. So the intensity is also increasing, and both the shorter wavelength limit and the position of the maximum shift to shorter wavelength. So here you can see the SWL, which is shorter wavelength limit, and the position of the maximum. So here for an example, for 5 kilovolt, the position of the maximum is this, and sorry, so position of the maximum is this, and here the position of the maximum is here. So the position of maxima is also shifting to the shorter wavelength, and the SWL is also for this the SWL where the intensity is 0, that is called the SWL. So that is also shifting towards the left. Okay, so here you can say more the number, I mean the more the voltage will increase, then more will be the intensity. Okay, so more will be the intensity, then there will be the more number of photons will produce per second. So the electron, I mean applied voltage. So when we applied voltage is increased, the number of photon produced per second and the average energy per photon are both. I mean both for number of photons and the average energy per photon both will increase, because when you will increase the voltage, I mean the acceleration will also increase. So that's why the intensity is also increasing, and that will lead to increase the photon produced per second. So the answer will be C. C is number of photon produced per second increase. So yeah, you were right. Now the second question is, target material in an X-ray source affects what? Intensity of the continuous spectrum, wavelength distribution of continuous spectrum, both intensity and wavelength distribution of the continuous spectrum. Neither affect the intensity nor the wavelength distribution of continuous spectrum. So can you answer for this also?
Is it C?
Okay, both intensity and wavelength. Okay. Anyone else? Just think about the relation. What is something from which the target material, which is anode, in an X-ray source will affects what? Target material will affect what? Just think there are
I
different
think
kinds of.
it's B, not C.
Okay, B.
Intensity is depending upon voltage, right? Based on the voltage of the
Yeah.
tube, then so it should be B, I think.
Okay. Anyone else wanted to correlate, or just think about the target material? There are different kinds of target material. Suppose if we will use the copper or the moly or the different something else, then what will happen? So in that way, it will be easier for you to understand this.
So maybe intensity of the continuous spectrum.
Huh? Which one?
A. Option A.
A. Okay. Fine. So one has said the A, and another one said the B. Fine. So anybody else wanted to guess or say something? Hmm? No? So we have two options, A or B. So probably this will be helpful for you. So let's see. So here what it is asking, target material in X-ray source affects what? So target material. So target material here, as you can see, the total X-ray energy emitted per second is proportional, okay, to the area under one of curves and depend on the atomic number Z, as I said, of the target. So we can take a different material of a different atomic number and the tube current, okay, which is I, measure of number of electrons per second. So the total X-ray intensity will be given by this AIZBM. So here M is constant and A is also constant. So here is what is left, the Z and V. So when the large amount of white radiation are desired, it is necessary to use a heavy metal, like usually we can use a tungsten as a target, as high as and as high voltage as possible. So for tungsten we can use a high voltage. So the target material affects the intensity, okay, but not the wavelength distribution of the continuous spectrum. So here this is saying that when we will use any target material, the target material affects the intensity, okay. So suppose if we will use some lower atomic number, then whatever intensity we will get, that will be different, okay. So intensity, suppose if we are using a tungsten, then this intensity will be different. If we will use a copper or the molybdenum, then this intensity will be different. Okay, but not the wavelength distribution of the. So here the wavelength distribution, suppose if you will use a 20 kilowatt or the, I mean whatever the voltage you will use, so the wavelength distribution of the continuous spectrum will not affect. Okay, so only the intensity of the continuous spectrum. Okay, so this is, here you can see the continuous X-ray spectrum emitted from a tungsten target for 4 different values. Okay, so only the intensity, target material affects the intensity, but not the wavelength distribution of a continuous spectrum. So our answer will be A. So I think somebody has said the A, and that is correct. So did you guys get it, that what I was trying to explain here, or any doubt? Okay, so it seems no doubt, but once again I'm saying that when we will use, suppose a target material of a different atomic number, suppose if we will use a higher atomic number, then the intensity for, suppose let's say you are using one target material which is a molybdenum and another is a tungsten. Tungsten is a higher atomic number which is 74 and molybdenum is less, so the intensity you will get in this will be higher. Okay, but the wavelength distribution across the different voltage will be not affected by the target material, whether you will use a different target material or the tungsten, but the intensity what you will get will affect by the target material. So that's what question is trying to, I mean say something about this. So the A. Okay, so the next one is characteristic X-rays are produced during what? Deceleration of high energetic electrons by atoms, electronic transition from outer cell to innermost cell, acceleration of high energetic electrons by atoms, ejection of valence electrons. So this is very simple, that maybe in the last, or maybe last to last lectures we have seen it, how this continuous and
B, right?
B. Okay. Anybody else wanted to give answer for this? No one? Okay. So this is very simple. Just I have explained, like suppose uh, while suppose the continuous spectrum which is caused by the rapid deceleration of electron by the target. Okay, so here this is saying the deceleration of high energetic electrons by atoms for the continuous, but it is asking about the characteristics X-ray. Okay, the origin of characteristics spectrum lies in the atoms of the target material itself. Okay, so let's say consider, suppose we take any atom and which will have various cells like K, L, M and so on, and the quantum number, as you all have seen in chemistry, like for K n equals to 1, L equal for L n equals to 2, for M n equals to 3. So what will happen if one of the electron bombarding the target, suppose the electron is coming and that will hit your target material with a sufficient kinetic energy, then it will knock an electron. So suppose here the electron beam is coming from the SEM, okay, and this will knock out an electron from the K cell. Suppose this is a K cell, this is nucleus, this is a K, leaving the atom in an excited high energy state. Okay, so after that, suppose it will come, it will knock out the electron, then one of the outer electrons, Suppose this is L cell, this is K, this is L. Outer electron immediately falls into the vacancy in the K cell. So when this will come to fill out the this vacant electron, and in this process emitting energy in this process, the energy will get emitted in this process, and the atom is once again in its normal energy state. Okay, so the energy emitted here is in the form of radiation of definite wavelength. So this energy will have in the form of, you know, radiation, and it will have a particular wavelength, and this is the characteristics K radiation or the characteristics radiation. So here this is nothing but due to the electronic transition. It is not because of the deacceleration of any electrons, or it's not about the acceleration of any electrons or by the ejection of a valence electron. It is because of the electronic transition from the outer cell, which is, let's say you can say L or M, to the innermost cell like K cell. So in this process the characteristics X-ray will produce. So this is the answer. So do you guys get it, what I have explained, or should I explain it again? Is it clear?
Yes, sir.
Okay, fine. So the answer will be B, the electronic transition from outer cell to innermost cell. In this process we will get a characteristics X-ray. So answer will be B. An increase in voltage beyond critical excitation voltage will result in what? Increase in the wavelength of characteristics line, shifting of continuous spectrum towards longer wavelength side, short wavelength limit shifts to longer to wavelength side, increase in the intensity of characteristics line. So can you answer this? Think.
It is D. Answer D.
Answer D. Okay. Increase in the intensity of character. Okay, fine. So what about others? Hmm? No one wanted to answer or give some guesses.
I think option C is sir. Short wavelength limit shifts to longer to wavelength side.
Okay. Okay, fine. Nice. So others also please give answer, and it's it's not like you will be guessing a wrong or the right, you will get any extra point. You just have to make it interactive. Okay. So that's what we want. So let's see. It is asking about an increase in voltage beyond critical excitation voltage will result in what? So let's see. So here you can see, suppose this is your X-ray intensity versus the wavelength. So we are increasing the voltage, accelerating voltage. So from 5 kilovolt we are initially giving, then we are moving towards the 10, 15, 20 and 25 and so on and so forth. So when the voltage on X-ray tube is raised above a certain critical value, sharp intensity maxima appear at certain wavelength superimposed on the continuous spectrum. So here you can see, suppose we are giving an X-ray accelerating voltage of suppose from 5 to 10 to 20. So in this, when you will see the continuous spectrum, then you won't find any kind of maxima. But when we exceed a certain threshold or the certain critical value, let's say a 25, so here you can see a sharp intensity maxima appear. So here you can see a K alpha and here also a small K beta, but here you can see a very sharp intensity of a K alpha, which is superimposed on the continuous spectrum, right? So they are narrow, and since their wavelengths are characteristics of the target metal used, they are called the characteristics lines. These lines fall into several sets referred to as K, L, M, etc. in the order of increasing wavelength. All the lines together forming the characteristics spectrum of the metal used as target. Okay, so here it is saying, so here it is very clear, I think. When we increase in voltage beyond some value, which is called a critical excitation voltage, will result in what? So here you can see is it an increase in the wavelength? No. Shifting of continuous spectrum towards longer wavelength. So here you can't see any, here you can't see a shifting of continuous spectrum toward the longer wavelength side. No. So here it is an increase in the wavelength of characteristics line. Wait. And on what else? Increase in the intensity of the characteristics line. So it is D. Although I have written mistakenly A, but it will be D. It is not showing any shift of the continuous spectrum toward the longer wavelength side. It is not short wavelength limits shift to longer to wavelength side. It is what? The increase in the intensity of the characteristics line. Okay, so here you can also see a sharp intensity maxima. Okay, so which is also called, this is a characteristics line. So here when you will go from a certain more than the critical value, about the certain critical value, then you will achieve a sharp intensity maxima. Here as you can see a K alpha that will superimpose onto your continuous spectrum, right? So the answer will be D. Now, which of the following spectral lines is most intense? K alpha, K beta 1, K beta 2, L beta. So if you know that what is K alpha, K beta 1, K beta 2, or how we can find it, then maybe it will be easier for you to answer this question. So can you answer this question?
A. Option A. K alpha.
Option A. Okay.
Option A, sir.
Okay. What about others? Hmm. Okay. So what is K alpha? K alpha, suppose, is what? So here K cell vacancy may be filled by the electron from any of the outer cell. Suppose let's say L, M, N, or anything you can say. Okay. So this is your K, this is your L, and this is your M, this is your N. So let's say in the procedure of electron transition, when the electron will come from L cell to K cell. So this will be K alpha. Okay. When the electron will come from your M cell to K cell, it will call K beta. When your, let's say here, when your electron will come in L cell from M cell, so it will call L alpha. When the electron will come from N cell to L cell, it will call L beta. So this is how you will define the naming of K alpha, K beta, or L alpha, L beta, like that. So K alpha and K beta lines is from filling the K cell vacancy by an electron from L or M cells respectively. So when the electron is coming from L cell to K cell, it will K alpha. From M cell to K cell, it will K beta. Again, there is a further distribution which is called a K alpha 1 and K alpha 2. So this is related to the electronic transition from S or P orbitals. Okay. So suppose the electron is coming from L cell to K cell. So that is called, what is that called? K alpha. In L cell also, if the electron is coming from the S orbital to the K cell, then it is called the K alpha 1. from the p orbital of L cell to K shell. It will call K alpha 2. Okay, so when the electronic transition from s or p orbital in the L cell towards the vacant K shell will happen, it will call a K alpha 1 or K alpha 2. It is possible to fill a K shell vacancy either from L or M, so that one atom of the target may be emitting a K alpha radiation while its neighboring is emitting a K beta. But it is more probable that K shell vacancy will be filled by an L electron than by the M shell electron. Okay, so that's why the K alpha line will be stronger as compared to the K beta. Right, K beta will be weaker, but the K alpha will be stronger. So here also you can say the intensity of the K alpha is higher as compared to the K beta. Okay, so here you can say the K alpha is for this is molybdenum, K alpha 0.7, and here this is a 0.6. So the K alpha will be the higher, or you can say a K or the higher, or the you can see the more it is asking about the following spectral lines is more intense. So the more intense will be what? K alpha as compared to the K beta. Okay, so is it clear to you all or not? I hope it is clear to you. So answer will be A, right? So next is Moseley's laws. The wavelength of any particular line increased as atomic number of emitter increased, decreased as the atomic number of the emitter increased, remained constant as the atomic number of emitter is varied, not related to the atomic number of the emitter. So do you know the Moseley's law? Then you may answer. What will be the answer for this?
B.
B. Okay. Anyone else? Anyone else? Moseley's law. The wavelength of any particular line, something related to the atomic number, wavelength and atomic number. Okay, so somebody has said B. Let's see. So Moseley's law, here you can see in the red line, the wavelength of any particular line decreased as the atomic number of the emitter increased. So it is inversely proportional. So wavelength of any particular line decreased as atomic number of the emitter increased. So here also you can see the atomic number is increasing. So here the wavelength is here lambda. So here you can see for the lower atomic number, this is for the higher range, and when we will increase the atomic number, this will be for the lower range. Okay, so for the wavelength of any particular line is decreasing. Okay, when the atomic number is increasing, then it is decreasing. So here you can see this is for the long range and this is for the shorter range. So here also this is some relation between the frequency, atomic number, and L lines are not always of long wavelength. So L alpha 1 line of a heavy metal like tungsten has about same wavelength as K alpha 1 line of, this is something factual. So here you can see the Moseley's law is the wavelength of any particular line decreased when the atomic number of the emitter is increased. So it is inversely proportional. So answer will be B. So filters are used in X-ray diffraction experiments. For what reason? What is the purpose? To remove K alpha line, to remove K beta line, to remove K alpha 2, K alpha 1, sorry, to remove K alpha 2 from K alpha 1, to remove L alpha and M alpha lines. What will be the answer? Hmm? Say something. This is also quite easy. I don't think so. It is very difficult.
Is it D?
What? D or B? What?
Last one. To remove
Last one.
L alpha and M alpha lines. Not
Okay,
sure.
okay.
It's a guess.
Okay. Anyone else?
B.
B.
Yeah.
Okay, fine. Okay, let's see. Okay, let me see. Where have I? Uh, yeah, fine. I thought I have misplaced the slide. So, uh, when you will do a X-ray diffraction experiment, so require a radiation which is closely monochromatic as possible. So, however, the beam from X-ray tube operated at low voltage, sorry, at a voltage above VK contains not only strong K alpha lines, but also it will consist your weaker K beta line in the continuous spectrum. As you can see here also in the 25 kilovolt, there is K alpha line and there is a very weak intensity of a K beta will also be there. So the main reason of this using, sorry, main reason of using this X-ray filter is to remove this K beta. We only want the K alpha. So the intensity of this undesirable component can be decreased relative to the intensity of the K alpha line pass, and we will when we will pass through it the filter. So we don't want K beta, we only want K alpha. Why? Because we want a monochromatic as possible. X-ray I mean the many which is the, like diffraction or the X-ray diffraction experiment that requires a radiation which is closely related to the monochromatic. Okay, so we don't want K beta. So because in the K alpha, when the K alpha will produce, then there will be K beta will also be associated, although the intensity of the K beta will be weaker as compared to the K alpha, but we don't want, we wanted to remove that. So that's why the main function of using this filter is to remove the K beta. So the answer is B. B is what? To remove the K beta lines. So which of the following is correct? Short wavelength X-rays are easily absorbed. Long wavelength X-rays are hard X-rays. Short wavelength X-rays are highly penetrating. Short wavelength X-rays are soft X-rays. So what will be the answer for this?
It is C.
Okay. Any other answer? Okay. So it is asking about the which of the following is correct. Okay. So short wavelength X-rays are easily absorbed. Long wavelength X-rays are hard X-rays. Short wavelength X-rays are highly penetrating. Short wavelength X-rays are soft. So short wavelength X-rays are highly penetrating, okay, and are termed hard. This is called also the hard. While long wavelength X-rays are easily absorbed and are to be said soft. So short wavelength, it means what? When you will use a short wavelength, that means the energy is high. So where the energy will be higher, the penetration will be also higher, right? So here you can see this bar. So this is the photon energy, right? So when the energy, here you can see short wavelength means, here you can see the wavelength is here increasing and the energy is decreasing, okay? And here the short wavelength, it means the wavelength is decreasing but the energy is increasing. So it is very obviously that when the wavelength of the X-rays is in decrease, the energy of the X-rays will increase. That will lead to give a high penetration, and this is termed as a hard. While when we will use a wavelength of a longer wavelength X-rays, then it will be easy to absorb, and that is called the soft. Okay, so answer C, short wavelength, which is a high energy X-rays, are highly penetrating. Okay, here it is saying the short wavelength X-rays are easily absorbed. No. Long wavelength can be easily absorbed. Long wavelength X-rays are hard X-rays. No. Short wavelength X-rays, because it is a high energy. So here you can see the short wavelengths are termed as a hard. So short wavelength X-rays are short X-rays. No, this is hard. So the only answer which is correct is the C. Short wavelength X-rays are highly penetrating. C. Absorption of X-ray is proportional to what? Only mass by density of the material, only thickness of the material, both density and the thickness of the material, natural bonding, nature of bonding in material. So, can you guess the relation? It's just simple. It's just a material thing. I mean, you just think about the absorption. So, what it could depend on? Like, there is only 2-3 options: density, thickness, mass.
It is A.
A, okay. So only mass by density of the material. Okay. So this is mass absorption coefficient. So here you can see in this formula, this is I, which is the I naught is the intensity of the X-ray beam and Ix is the intensity of the transmitted beam. So here the intensity is coming of I naught intensity and the Ix will be the after passing through the thickness of X. So let's say the X is the thickness. Okay, and linear absorption coefficient mu is proportional to the density. So absorption coefficient is proportional to the density, right? But also if you will see, suppose if you will vary the thickness, here you can see saying the mass absorption coefficient. This is the mu by rho is called the mass absorption and is constant for the material and independent of any physical state for the liquid, solid or gas. So C, okay, so C is what? This is, here it is saying the absorption coefficient mu is proportional to the density. So suppose if you have, let's say, a material of a very high density and you will give any radiation of a I naught intensity, then you will get variation. Suppose material A is having a high dense as compared to material B, then the intensity will also vary when it is coming out. Fine. In the same way, when you will use a material of a, let's say, a thickness of 1 centimeter and the thickness of a 5 centimeter, then the intensity of emitting and the passing or the coming out will vary. Okay, so it will depend on the both density as well as the thickness of the material. Okay, it is very common absorption of X-ray. So both density and the thickness of material is something that will affect the absorption of your material. So this is in this figure, you just say, suppose you are giving 100 photons. So on the thickness of your material, if my material will be more thick, then the coming photons which will come will be lesser as compared to the thin material. In the same way, if you will use a high dense material, then the number of photons coming out will be lesser as compared to the less dense material. Okay, so absorption is something which is depend on both the thickness, which is here it is giving through the thickness, and the density, which is rho. So it depends on the both. Okay, a very quick numerical. It's a very simple, and I want you to solve it now. So it's just very simple, and it is asking about the minimum wavelength of X-rays, and what is given here, the accelerating potential of an X-ray is what, 40 kilovolt. So can you just quickly do it? Maybe if you have a mobile near you, and just do it very quickly and let me know the answer. Are you guys doing? Let me know the answer. I have to write here. Tell me the answer.
Is it 0.031 nanometer, something like that?
0.031 nanometer. How have you calculated this?
Yes, it is that lambda SWL is equal to 12.4 and 10 cube divided by V. That is a relation.
What?
And we need to lambda minimum is
Huh?
equal to 12.4 into 10
Oh,
power minus 3 divided by V.
okay, fine. Okay.
So
So
substituting the value of V
is
as
anyone else also attempted this? Maybe you will find in your assignment some kind of question like this. Very simple. No? So here, yes, you are right. So here you can see that it is the relation lambda SWL, short wavelength, or the lambda minimum is given by what? When you will place HC by EV, then when you will place all the value of HC and E, then it will come around 12.40 and 10 is to power 23 upon V. So V is given 40 kilovolt, right? V is given 40 kilovolt. Then you just have to simply put your value. Very simple. Okay, so the answer will be like 0.31 or 0.32, like that. So that's it. You just have to put the value V, which has already given.
say I have a doubt here. Is the relation 12.4 divided by 3 right? Or is there
Huh?
any correction in that formula? I have a doubt here. See, can you explain the unit of substitutions here? Because I find
Unit,
it.
I think so. Here this is in the volt. So it is given in the kilovolt. So you just do what you have to do, the 40 kilo. So 14 to 10 is to power 3. 10 is to power 3 cancel by the 10 is to power 3. So that 12.40 is divided by the 40. That will come around 0.3, 0.31.
Okay, so suppose if we have the lambda value is in nanometers, say point something like that, 0.03, something like that. So we have to substitute. If you want to find out the value of voltage, then we have to substitute it as say 0.31 into 10 to the power minus 9, right?
What?
Say here what they have given is the voltage, and we are asked to find out the X-ray wavelength, right, in nanometers.
Yeah.
So So we have to, for this relation, we have to substitute the value of lambda in meters, right?
No, no, no. That is in nanometer only. See here,
So yeah,
this is in nanometer only. No need to change.
yeah. That's
Okay,
the reason
whatever
I
you are
asked.
using here, that is in nanometer. Here, this is in volt.
Yeah.
Okay, so you just have to simply 12.40 divided by 40. That will come 0.31. So here that is already nanometer. No need to. It is not in meter, or you don't need to change in meter. It is asking even about the nanometer.
So the relation that we have given, that means 12.4 10 to the power of 3 divided by V, you will get the value of lambda in nanometers.
Nanometer,
So
right?
every unit conversion is be taken care. So
Yeah, yeah,
that
yeah.
the details about the unit was missing in the material. That's the reason I asked.
Okay, yeah, 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 yeah.
Because in the internet, I find a different formula, means a slightly different one, 1.24 10 power minus 6 divided by lambda minimum. So that's the
Okay,
reason
yeah.
I asked you whether is there any change in the
Okay.
equation.
Yeah, yeah,
So
yeah, yeah.
okay,
Is
thank you.
it clear? Is it clear to you all? Also, other people? It is very simple. Okay. So just solve it and get it done. So fluorescence yield is what? Higher for low atomic number, low atomic number, lower for low atomic number, higher for high atomic number, or the lower for low and higher for high. So can you also give the answer for this? What will be the relation between the fluorescence yield and the atomic number? Which will be the correct? Hello. B. Last D. Okay, fine. So let's say this is that slide. It is the Auger process can be found from the fluorescence yield. So where the vacancy is caused by incidental. So this is, suppose here you can, let's say this fluorescence yield is equal to number of atoms that emit K radiation by the number of atoms with K cell vacancy. So here what it will come when you will calculate the fluorescence yield will be 0.03 for the magnesium. The atomic number for the magnesium is 12, and when we will increase the atomic number, then the fluorescence yield is increasing. Let's say 0.03 to 0.41 to 0.77. So here you can see when the lower the atomic number, lower will be the yield. Higher the atomic number, higher will be the yield. Okay. So yeah, someone has said very correctly. So lower for the low atomic number element and higher for the high atomic element number. So which is correct? Which of the following is incorrect? Or Auger effect is a three-level electron transition. Kinetic energy of Auger electron is related to energy difference between the transition states. Kinetic energy of an Auger electron is characteristics of that atom. Binding energy of an Auger electron is characteristics of that atom. So which one is true? I think I can see a pretty much. It is not very difficult. Maybe two options are very clear. Maybe you can get confused. So it is asking about which one is incorrect. So just think about which one is correct. Then one is already incorrect. Can you give me the incorrect answer? No.
Is it A?
Okay. So here you can see um, this is here the K cell vacancy is an ionized high energy. It can lose the excess energy and return to the normal state in two ways. By emitting the K radiation, so production of characteristics radiation, or by emitting an electron, which is Auger effect. Okay, so it is not something which is depend on the binding energy. Here also you can see the first one is a three. What is first? Auger effect is a three level transition. So which is true. Okay, so here you can see here it will some atom will come and then this is 1 2 3. It is a three level electron. When you will see the lecture, then you will get to know how the this Auger electron will get produced. Okay, so it is a three level of electron transition. Then what it will the next was one was what kinetic energy of electron is related to energy difference between the transition which is obviously if you will change the kinetic energy of your incident your Auger electron, so the energy difference of the transition state will also vary. Kinetic energy of an Auger electron is characteristics of that atom. So yeah, this is what characteristics production of a characteristics radiation. Okay, so the ejected Auger electron has a kinetic energy related to the energy difference between this. So the electron that do escape have kinetic energy related to the difference between energy levels of parent atom. That is, their energies are characteristics of that atom. So what it is saying, the energies are characteristics of that atom, not the binding energy of an Auger electron is characteristic of atom. Kinetic energy, not binding. Kinetic energy of an Auger electron is characteristics of that atom. So the incorrect will be the binding energy of an Auger electron is characteristics of that atom. So this is something that you have to see in this slide for the better understanding. So yeah, D. X-rays are used in diffraction experiment have wavelength in the range of what? This is very pretty simple. I have just shown you the bar. So
First, option A.
option A. Okay, right. This is very quite obvious. So I will not give a much time. So here you can see this is what it is asking the wavelength. So here you can see this is a wavelength in angstrom. So where the x-rays are held here, so this is somewhere, so this is a 0.5 to 2.5. okay, in this range. Okay, 0.5 to 2.5 angstrom. Okay, so here your x-rays are live, the wavelength 0.5 to 2.5 angstrom. A. So this is again the same question which I have included. So, which type of radiation is used in analyzing crystal structure? Okay, which type of radiation is used in analyzing the crystal structure? Can you give something? I have shown you maybe three, four, maybe a no, a 2 or 3 class back. There was one peak picture of the interaction volume where the Auger electron is coming, secondary electron is coming, characteristics is coming, Bremsstraum this Bremsstraum longest radiation is coming. So for the crystal structure which we can use, do you guys remember it? No? Do you know that for what information Auger electron gives, what others, what secondary, what backscattered? Hmm? No. If no, then I will leave this question for you and just go through that lecture again or just see the current lectures also. You will find it out and let me know in the next class. So this I will leave as a homework question. Fine. So I will not explain it. I have the some slides, but since I have explained it in the previous classes, but maybe you guys are not giving, then I will request you to please see that lecture, and so that you can also revise that, and maybe it will be helpful for you to brush up some old concepts. And this is very easy. Somewhere I will also show you the slides where okay, let me just check. It is very um, I do not know. I also having, yeah, something like this. Okay. So here you can see some kind of this kind of a slide where I have explained that what information it is giving. So here you can see a continuous X-ray which is per long. Here the characteristics X-ray. Here the Auger electron. So in this way you can find that from where we can get that information. It's pretty much simple. Okay. So yeah, that's all for the today, and let's um, yeah. So these are a few questions that I have prepared for this week, and I hope you guys have a better understanding for your assignments question. So let's meet next week, and let me sorry, and please give me the answer for the question that I leave left, and we'll meet again. So do you guys have any questions from the today's presentation, or any questions you would like to ask?
So I have a small question.
Yeah.
What is the is there any use with the white radiations?
What?
White radiations.
Okay. So what is your question?
So what is the use of white radiation? Or is it having any particular use, or is it just a part of the process?
I do not know in what sense you are asking this question, because directly if you will say a use of white radiation, then it should have some context that on what I mean. Is it related to what? So then only I can give some comments, because white
I'm asking,
radiation.
we are using the K alpha radiation for some particular applications or from some purpose. So during the process, we are getting some white radiations also. So
Okay.
what is the significance of this white radiation, uh, or is it affecting any process, or is it a disadvantage, or asking some features about this white radiation?
That also I have to check, because I do not know. I mean, regarding what you are asking, white radiation, I also have to see that where it is coming, and what it is giving. So that I will check, and will see. Okay.
So,
So I.
one more question.
Uh,
It is regarding one of the questions that is asked in the assignments. So, there you have asked about the X-ray, which is used for the diffraction and for the uh, characterization of crystal structure. So, can you comment something regarding the diffraction and the X-ray use of X-ray technique?
What question you are asking?
No, in the assignment question, there is one question which is asking about the nature of X-ray that is used for diffraction or something like that. I'm not sure whether it's diffraction or something like that. So,
But I do not
one
know,
question was there.
because I cannot answer like this. Means I have to, see the what are the answers available, and also in what context they are asking. So all that I have to see. But yeah, let me. Sorry. I will. Let me show, or I will give you this screen sharing. Then you show me the questions in the next class, and probably we will discuss there. Okay.
So it's given something like this. For diffraction purpose, which of the following sources are used? It's following sources are used: polychromatic X-ray, inelastically scattered electrons, white X-ray radiation.
For this, you have to
X-ray.
go through the lecture. You will find it in lecture. You have to see the lectures. Have you watched the lectures?
Yeah, I have completed almost 3 to 4, I think. Yeah, one more is left.
Okay, so just see the lectures and let me know, because it's your assignment and you have to do.
Yeah, I know, but still I'm got some confusion regarding this.
Yeah,
That's
yeah,
the
yeah.
reason why I asked you about the white radiation.
Okay, yeah. So we'll do one thing. Just watch the lectures completely and ask me in the next class, or show me the questions. What are the questions are there? Because I have not seen your lectures, to be very frank, and I'm just taking from the old assignments question, and I'm just trying to explain why. Because I want, the main purpose of this session is to clear your doubts, which can be helpful to solve your current assignment, right? So that's why I'm taking the similar question, which at least, if you are not seeing the whole the lectures even, or if you are having some doubts in the some concept, then maybe I can be show some slides and try to get you understand on that topic. So that's the main reason of this session. So anyway, don't worry, for now you just see the lectures, and even though if you won't get, then let me know in the next class, we'll discuss it. Okay.
Hello, sir.
Yeah.
Can you suggest a good text to refer?
What can?
A good textbook to refer
Okay.
the subject.
For which subject?
On material characterization. Good
Okay, okay.
textbook. So
Okay. I'll do one thing. I have a few books, but currently I forgot the name and the title of the book and the author of the book. But I have few, so I will share it with you guys in the next class. I will write in the chat box, and which will be helpful for you to after class you can read that and you will have a better understanding. So surely I will do that. Thanks for reminding.
okay, thank you.
So you just remind me in the next class also if I forgot.
Okay, thank you. Sir, regarding one doubt.
Yeah.
Regarding the problem, in that acceleration potential 40 kilowatt, so we have to find out the minimum wavelength.
Yeah.
So when we substitute that, we will get 12.40 into 10 power 3 divided by 40 kV. So I'm getting an answer of 310.
But that is 40 kilovolt. Now you have to change 40 kilovolt to volt. So 40 into 10 to the power 3.
Okay.
Yeah.
So okay. Then it's
yes.
okay.
Yeah.
Okay, thank you. Thank you.
Yeah. Okay. Okay, then see you guys in the next class.
Thank you.
Yeah. Thank you.